Hello everybody. This week we are talking about circuit analysis, and specifically we're applying this to a capacitor network. One of the main results that we will use, and that you can use for any linear circuit, is Thevenin equivalence theorem, which states that any linear circuit can be simplified down to an equivalent circuit, where that circuit is a combination of a voltage source and a linear circuit element. This means as long as we have a circuit that's only composed of linear circuit elements and some sort of voltage source, we can simplify our picture into something that's easier to work with. The important thing here is that by doing this using a Thevenin equivalence, the only downside to this is when you take a more complex circuit and use this theorem to turn it into something that's simplified, you do lose information. So when you apply this, you have to be careful that when you do so, that you don't simplify the circuit too much to lose the information that you may want about a specific component. And the important thing is that Thevenin equivalence can be applied any number of times to get any number of equivalent circuits, as long as those elements in the circuit are linear. And by a linear element, I'm talking about components such as resistors, capacitors, and inductors. Other things that wouldn't necessarily work are nonlinear elements, such as like a diode, or certain gas discharge tubes, and semiconductor components, and things that are not as simple and straightforward. So we will use Thevenin equivalence and the definition of capacitance, together with some other things, to analyze this a capacitor network circuit as such in the window here. So in this problem, we have three capacitors that are across a potential difference between A and B of 12 volts. And we're given a capacitance of each one of these capacitors. And what we want to find is the equivalent capacitance of this network. So what we want to do is apply Thevenin equivalence. So in this part, we have A and B connected by a voltage source at 12 volts. And we want to transform this circuit into something like this, which is what Thevenin equivalence says we can do. Which says that we can take this voltage source and linear elements and turn it into a voltage source in one element, where the capacitance of that element is now the equivalent capacitance. So you can actually take this in steps if you would like, and it will be useful to do so and to demonstrate to yourself that you understand how to apply this. So what you can do is take this capacitor network where 12 volts is applied, and first simplify one section of the circuit. That's what I'll do here. So what we would need to do is we leave this as C1, and now take these two capacitors in parallel and get an equivalent capacitance and an equivalent circuit. And then what we can do again is apply Thevenin equivalence again to just get the voltage source in series with one element, where that is the equivalent capacitance. We'll call that capacitance, equivalent capacitance subscript 2. And so in order to get what C equivalent 1 is, we have to know how capacitors in parallel add. and they add the opposite way as resistors add in parallel. Because resistors in parallel, as you know, when you get an equivalent resistance, they add like so. For capacitors, and then that's in parallel for resistors. In series, they just add together in a linear fashion. For this in case for two resistors in series, and this is for two resistors in parallel. Capacitors are the exact opposite, which is related to the definition of capacitance as the total charge, or not total charge, but charge on the plate divided by the potential difference between the plates is the capacitance. And so if we want to get an equivalent capacitance for two capacitors in parallel, capacitors add in parallel like resistors do in series. And so C equivalent 1 here is going to just be equal to C1 plus C2. Now if we want to get a secondary equivalent capacitance, it's C1 and C equivalent 1 in series. And now these add like resistors in parallel. And so C equivalent 2 is 1 over C1 plus 1 over C2 plus C3, where this is just our C equivalent 1. And so we can get a common denominator here and add them, and you get C1 plus C2 plus C3 over C1 times C2 plus C3. And then we can invert that to get C equivalent 2. And that will be C1 C2 times C2 plus C3 over C1 plus C2 plus C3. And that will be our second equivalent circuit. And now we can use this here with a problem, and we can get a equivalent capacitance. And that equivalent capacitance, given our numbers here in microfarads, will give you an equivalent capacitance 11.9 microfarads. And that will be the answer to part A, or the first question. For the second one, for the other question, it asks about the charge on a capacitor C1. So now what we want to find out is how much charge accumulates on the plates of the parallel plate capacitor. Important thing to know, I want to point out before going any further, is if we have parallel plate capacitors, some amount of parallel plate capacitors in series added, where we say maybe the potential difference across this series of capacitors is 12 volts. Well, we know that this is conducting materials, right? So in the conductor, in this wire, in this circuit, right, that free charges are allowed to move. And so these charges see a positive potential difference, and this will cause charges to move towards that potential difference, right? Because again, when there's a potential difference, there's an electric field. And if there's an electric field, then charges are moving, right? And they want to move in a way to eventually reach some sort of equilibrium state, some stationary state, some static state, where charges are no longer moving. Because in this case, now that we're dealing with series and we're dealing with currents, we're dealing with current densities. And if we're dealing with current densities, current density is charge over time moving through space. And so we're no longer in circuit analysis, we're no longer dealing with an electrostatic situation inside a conductor. We're dealing with currents, and so we're dealing with charge is moving. And so we're dealing with really an electrodynamical situation. And that means that charges are moving, and that creates current, right? So we have this potential difference across a capacitor series network. And so charges will want to move towards that difference. And so we will see charges start to accumulate, right? They will move as much as they can towards this difference. But once they reach this plate, in between the plates is vacuum, right? Or a dielectric, such as glass or some other material. But either way, whether it's vacuum or if it's a dielectric, only a certain amount of charge can accumulate on the opposite side charge plate. And at some point, it's going to be more energetically favorable for these free charges to stay where they are or move further away from the plate. But once it reaches that state, it's clear that any free charges within this part of the conductor, between the two plates in series, will see a net positive or negative charge on this plate here. And so they will move away from it. If this charge on this plate is positive, then positive charges that are over here will want to move as far away as they can. And so you'll get a cascading effect where if this is positive, other positives will then start to accumulate on this side. And this will cascade all the way down, where the charges on that plate will be equal. And so this leaves the other plates polarized, equal and opposite charge. And so when you have capacitors in series, the charge on one plate, they're all the same. Mind you that the total charge on both plates put together will be 0, right? If there's a positive charge here on this plate, then whatever's on this plate will be equal and opposite, since this is a conducting material. And so if you would take a Gaussian loop around here, the total enclosed charge on a capacitor, in this case, is equal to 0. But on any individual plate, if I were to enclose a Gaussian surface around just the one plate, it wouldn't be 0, because the charges accumulating on each plate are equal and opposite, due to the fact that this is a conducting material with free charges that are able to see this potential difference. And then because they see that, quote unquote, see that potential difference, they move in order to reach a new equilibrium state. So this is important, because that means if we have a circuit, capacitor network here, that in the case of, say, this second equivalent circuit, that whatever charge is on C1 is also the charge on C equivalent 1, because they're in series. And as we just argued, that two capacitors or any number of capacitors in series will have the same charge on the plates, right? This is positive, and that's negative, and that's negative. But we can exploit that to be able to get the charge on the capacitor C1, since we know that the potential difference overall in this circuit is 12 volts. And so that's what we'll use in order to figure out the charge on capacitor C1, is we'll use that second equivalent circuit that we drew. So in this case, we can look at Kirchhoff's voltage law for this equivalent circuit, right? So we have 12 volts voltage source, and then we have a voltage drop across capacitor C1, right? This will have some voltage drop, and this will have some voltage drop. So we say the C equivalent 1 and V1, delta V1. We can rewrite, we know that due to Kirchhoff's voltage law, loop law, that this positive 12 volts voltage source minus V1 minus V equivalent 1 will have to equal 0. That's Kirchhoff's voltage loop law. Now we can rewrite these in terms of the capacitance, right? Since capacitance is equal to the charge over the change in potential, we can write that as the change in potential is equal to the charge over the capacitance for any one capacitor. Delta V1 and delta VQ1 as Q over C1 and Q over C2 plus C3, since they're the same charges. And so when we factor out the Q, get this, and then we can divide that over our 12 volts. And that will be what our Q1 is. And this will work out to be 142.8 microcoulombs. And that's the charge on the second capacitor. Now, next thing we're going to do is get the potential difference across C1, which now we can do just by definition of capacitance, right? That'll just be the capacitance is equal to the charge on a plate divided by the potential difference. And we know C1, and we know charge Q1 from that part. And so that implies if we divide over the C1 and multiply it over to delta V, that delta V1 is equal to the charge over the capacitance, which is then equal to 9.5 volts. And so that is the potential across that plate. Now, what if we want to get the voltage across C2 and C3? This is where, when you take the equivalence, where you may or may not miss something. Important, right? Because if we go all the way to this third picture for the third equivalent circuit, by breaking down this 3-component network to a one singular component network, we lose information that we need about C2 and C3. But if we go to this intermediary equivalent circuit that involves a equivalent voltage drop across an equivalent capacitance for the two in parallel, and then remember that the voltage for any elements, the voltage drop across any elements, linear elements in parallel, has to be equal, which comes directly from Kirchhoff's loop law, that means that the voltage drop across C2 and the voltage drop across C3 are the same. And thus, if we get the voltage drop across this equivalent capacitance in this second picture here, that would be the same as the voltage drop across C2 and C3. Thus, we can directly use the voltage loop law, which says 12 volts, minus the drop on C1, which we just found as 9.5 volts, minus the voltage drop across that equivalent capacitance has to equal 0, then that equivalent voltage drop, which is equal to delta V2, which is equal to delta V3 because they're in parallel, is equal to 12 volts minus 9.5, which is 2.5 volts. And so we have the answer for that. Now to get the charges on the capacitor C2 and C3, we can directly get, since we know the voltage drops, and by definition, if we know the voltage drops and the capacitors on those, we can get the charges on the plates. Now there's another question which asks about a parallel plate capacitor consisting of rectangular aluminum plates of certain areas and a potential drop across them. And in class I went through the derivation of the formula for how to calculate the capacitance for a parallel plate capacitor. And I'm not going to repeat it here, but we know that that is equal to this formula where D is the distance between the parallel plates and A is the area of the plate. And we're assuming that the plates are parallel plates and they're squares. So actually, we're not assuming they're squares, but we're assuming they have some area and it's either it's some sort of rectangular shape and they're in parallel, and that's why we draw capacitor elements like this, even though they're not always parallel plate capacitors. There's different type of capacitors, but this is a simple one in which I derived a formula for in class using Gauss's law. And so we can directly apply that here, just being careful that in this case there's a dielectric in between the plate, and so then instead of epsilon naught, we have just the epsilon, where that's going to be the dielectric. We have to relate that to the dielectric constant. And so we can rewrite this in terms of kappa and epsilon naught for a capacitor with a dielectric in between. And that makes up this worksheet. I hope that helped. Just remember that Thevenin equivalence is really powerful and useful tool that you can always use for any linear element circuits. All right, appreciate it. Thank you.